Welcome, students. This is our first video in Calculus 1 lecture series. Today, we are going to give a brief introduction to limits. We are going to study informal definition of limits, one-sided limits, connection between one-sided and two-sided limits, and infinite limits. So let's start. A bunch of ideas in calculus arose from the following two problems. And first one is a tangent line problem. Given some general curve f, we would like to find an equation of tangent line at point P. Second one is an area problem. Again, given some curve f, we would like to find an area underneath it. Let's see how limits are connected to these two problems here. We will start from tangent line problem. Here we have a graph of f of x, and we'd like to find an equation of tangent line at point P. Our approach is going to be the following one. We are going to select some arbitrary point Q on f of x, and we'll start moving closer and closer point Q towards point P along f of x. And we are going to see what's going to happen to the second line, line that passes through both points P and Q. So as we can see, when we move Q closer and closer to P, second line is going to approach to a tangent line. Let's use that approach to find an equation of tangent line, let's say to a parabola y is equal to x squared at point, let's say 1, 1. Let's define the slope of tangent line as m tan. Then it is equal to y minus 1 over x minus 1, since an equation of tangent line is passing through point P. If we knew the slope of our tangent line, then we would express an equation of tangent line as follows. As we said before, we are going to take an equation of secant line, and as we move our point Q closer and closer to P, that equation will approach to an equation of a tangent line. So the slope of secant line will approach the slope of tangent line. And let's express the slope of secant line as secant. Which is given as, if we choose some arbitrary point x for x coordinate of that point Q, then its y coordinate is going to be x squared. So it passes through point x squared, through point x squared and x, and through point 1, 1. So it's an equation for the slope of secant is given as x minus 1 over x minus 1. All right, so we are taking a limit of it as x is approaching to 1. And as we said, slope of secant line is going to approach the slope of tangent line. So we can replace that with m tan, which is going to give us two. So the slope of tangent line is equal to 2. So here we have an equation of our tangent line. Our second problem is an area problem. Here we have to find an area under the curve, which is defined by y equal to f of x. This can be done using the following procedure. So let's assume that we'd like to find an area under y is equal to f of x on the interval from a to b. Then we can start by splitting this up into intervals of, let's say, of equal length, and then we are going to approximate the area under our curve by the areas of the following rectangles. Then, as we can see, if we increase the number of these subintervals, we'll get better and better approximation. So if we take limit n, let's say n denotes the number of intervals as n approaches to infinity, then we'd get exactly the area under of our f of x curve. So we'll get to the integration in more details in chapter 5. So we can see that limits also arise in area problem. Now we are going to give an informal definition to limits if the values of f of x can be made as close as we like to L by taking values of x sufficiently close to a but not equal to a, then we write limit as x approaches to a of f of x is equal to L. This can also be expressed using the following notation here. This definition can be made more rigorous by elaborating more by what do we mean by can be made as close as we like, and also replacing this statement here sufficiently close to a by showing how close to a. The more rigorous definition is known as epsilon delta definition. However, we are not covering it this semester in Calculus 1 course. So this is also known as two-sided limit. Since here we can approach to a from both sides. If here we have graph of our f of x and a is a point of interest where we'd like to find the limit, then we can approach to a from both sides. However, various functions will behave differently when we approach to a specific point from left or right hand side. Let's take a look at the following function. F of x is equal to absolute value of x divided by x, which is equal to 1 when values of x are greater than 0 and minus 1 when values of x are less than 0 and undefined at 0. So let's take a limit as x is approaching to a from the left side. So the graph of this function looks like a step function, but not defined at 0. So minus 1 when negative and 1 value when values of x are positive and undefined at 0. So when x is approaching to a from the left side, then limit of f of x is equal to minus 1, and when limit x is approaching to a from the right hand side, then limit of f of x is equal to plus 1, which brings us to the definition, informal definition of one-sided limits. This is similar definition to previous one. Only thing here we add a small detail on how do we approach this value of a. So if the values of f of x can be made as close as we like to L by taking values of x sufficiently close to a, but greater than a, then we write limit as x approaches to a from the right side of f of x is equal to L. And similar definition for left side limit for sufficiently close to a, but for values of a less, for values of x less than a. It's not always guaranteed that function f of x will get closer and closer to some single real value when x approaches to a either from left side, right side, or from both sides. In these cases, we say that limit doesn't exist. And the relationship between one-sided and two-sided limits is following. So the two-sided limit of function exists when both of it, left-sided and right-sided limits exist and they are equal to each other. So basically, a limit as x approaches to a of f of x is equal to L, if and only if a limit as x approaches to a from left side is equal to L and equal to limit as x approaches to a from right side. So looking at our previous example here, one-sided limits here exist, but they are not equal to each other, meaning that in this case, two-sided limit doesn't exist, and we can use the following notation for that. Well, if we get too technical about it, then a limit, let's say, as x approaches to infinity of a function, let's say simply x, this limit doesn't exist too, since there is no limiting value to f of x, and there is no single real number to which our function of x gets closer and closer as x approaches to infinity. So there is no limit to our function. So in that case, if we say that limit doesn't exist, we are correct. However, for the sake of simplicity in this course, when solving problems, I would ask you to write this limit as, let's say, if x approaches to plus infinity, as plus infinity. And when limit, let's say, x approaches to minus infinity for x, this limit here also doesn't exist, and you would be correct if you say that this limit doesn't exist, but when solving problems, express it as minus infinity. Right now, a couple of words about limits at infinity. Those two expressions here, limit as x approaches to a from left side of f of x is equal to plus infinity, and limit as x approaches to a from right side of f of x is equal to plus infinity. It denotes that f of x increases without bound as x approaches to a from the left and from the right sides. So if both true, then we write that two-sided limit of f of x is equal to plus infinity. And similarly, when one-sided limits are equal to minus infinity, we say that two-sided limit is equal to minus infinity. Now let's take a look at a couple of examples of infinite limits. Here we have graphs of some functions. The first function here, we see that left-sided limit as x is approaching to minus a, I mean a from left side, 1 over x minus a is equal to minus infinity, and right-sided limit as x is approaching to a from right side of 1 over x minus a is equal to plus infinity. So these two are not equal to each other. In this case, we say that two-sided limit doesn't exist. And limit as x is approaching to a doesn't exist. Here, left-sided limit is equal to plus infinity, and right-sided limit is also equal to plus infinity. And limit, two-sided limit in this case is equal to plus infinity. And here left side limit is plus infinity, right side limit is minus infinity. So two-sided limit doesn't exist. Here left side limit is minus infinity, right side limit is minus infinity. So we express that two-sided limit is equal to minus infinity. Now, a couple of words about vertical asymptotes. Here we have graphs of some functions with vertical asymptotes at point A. And so if a function increases without bound or decreases without bound as x approaches to some point A, then we call that line x is equal to A as vertical asymptote. Maybe example like this here. In this case, function of f(x) also has a vertical asymptote at A. So that will conclude our first lecture on introduction to limits.